Thank you. Thank you for coming to the last part of my lecture. As promised, I'm going to be talking about points 2 and 3 on that slide. That is, my plan today is to give you a very efficient algorithm for constructing absolutely normal numbers. I'll remind you a little bit on the way. And then I'll also like to look at fractal geometry. So from the beginning, I was presenting effective dimension as an interesting tool. In this particular lecture, focus on computational complexity problems. But actually, what happens, I think, when a topic gets really mature is that you kind of export it. So I think what's happened is that we have started very recently to be able to prove new results in fractal geometry using this effective dimension idea. So I want to talk a little bit about this, probably not in a very detailed way, especially the fractal geometry results I will present. I will not be very detailed, but I like to show you how they look like. So let's start with the algorithm. So yes, remember, we are looking at normal numbers. So for instance, in binary, they are infinite binary sequences, and the statistics need to be right. So 0 appears 50% of the time, 1 50% of the time, and for longer finite strings, the usual. So each of these appears 25% of the time, etc. So if these statistics are right for finite strings of any length, you have a normal sequence. In this case, a binary normal sequence. And absolutely normal is defined for real numbers. So in each particular base, you represent the number as an infinite sequence, and the statistics have to be right. So I promise you, I talk a little bit. There exist efficient algorithms as efficient as n squared polylog n steps to produce the first n bits of an absolutely normal real number. And I'm going to try to take this down to nearly linear time. And as I think I already mentioned, that nearly linear time is quite far more robust idea than linear time. So, well, I will use base B. So we are not in binary anymore. It depends on the base we're looking at. So base B is just B symbols alphabet. Notation is about the same. And S scale, which you probably have, even if you were not here in my lectures, you have seen it before, is a function. And this is the fair condition. It represents a betting strategy, and the fair condition is modulated by ds. And S scale, ds is here. And well, you might be more familiar with Martingale, which is a 1 Gale. And the success set is the set of infinite strings for which the lim sup of the d, of the value of d over length n prefixes go to infinity. So it's a lim sup thing. So you succeed in the best case. So of course, S-Gales and Martingales are related very easily. So for instance, if D is an S-Gale, then D prime defined by multiplying D by B to the 1 minus S to the length of the input. This is a Martingale. Okay, so what is the relationship between this absolute normality and these Gales, Martingales? Well, first observation is that if X is finite state, well, no, this is not a, sorry, this is not a normality yet, but yes, the definition finite state random means that no finite state Martingale succeeds on X. And well, you can notice that if dimension is less than 1, that is if you have an S scale for S less than 1, then you are not random. Okay, well, yes, looking, sorry, wrong direction. Yes, looking at the relationship between Gales and Martingales. If you have a succeeding S-Gale for S less than 1, then you have a succeeding Martingale, of course, and you are not random. Okay, why finite state randomness? Because it coincides exactly with normality. Okay, this is known since 72 at least by Schnorr and Stim. They already realized that finite state martingales define normality. So, well, this is just an explanation that, yeah, somehow you see that if the statistics are not right, so if you have a particular finite sequence that appears too often or not enough, it's kind of easy to see that a finite state automata would be able to trace this and bet on it and make profit on it. Because it's just a finite string. So it's just, you just need enough states in the automata to kind of follow this W and kind of count. Well, there's ways to do that. And also, the first observation is that this paper by Schnorr and Stim, they don't only show that normality corresponds to finite state randomness. They show far more, actually. Because if a sequence S, that is a sequence in alphabet of B symbols, if it's not B normal, then some finite state-based B martingale succeeds exponentially on S. So the growth rate of this martingale is very high. So they prove more than randomness. And on the other hand, if it's not normal, then no finite state base B if it is normal, then no martingale succeeds. And actually, that's also a bit more extreme than that. But what we really need is this part. So if S is B normal, then S is finite state random, okay? But if it's not B normal, then the finite state dimension is less than 1. So this is what is really convenient for us if we want to really construct quickly normal sequences, that the properties they have make them easier to detect. So, well, in particular, we remark that finite state dimension corresponds to normality. So finite state dimension 1 is equivalent to finite state random, and it is equivalent to being normal. Okay, this is one base. I'm talking only about one base. Okay? So this is what I'm going to use. I'm going to try to construct something that is absolutely normal by using these two properties. In particular, I will try to avoid this. I will try to construct something that is dimension 1. What I'm going to do, so somehow if I wanted to just use this finite state dimension or randomness concept, I would have to deal with all the finite state devices. So first thing I need is some sort of universal object in order to deal them all together. Okay? But I already mentioned that yesterday. Lempel-Sieve algorithm kind of serves this purpose. So this is what I'm going to use. So my objective is to compute an absolutely normal number fast, normal in every base. We need to construct a single real number, and we will use the Lempel-Sieve algorithm because this is kind of universal for normal sequences. But I am still talking about a single base, okay? So still Lempel-Sieve is Lempel-Sieve for this particular base. It doesn't magically give me all bases together. So, well, just to kind of at least give some credit, even the Lempel-Sieve compression algorithm was later converted into a base B Lempel-Sieve martingale. I think this is at least further in 1991. So this martingale kind of corresponds to the strategy described by the compression algorithm. I think I'm going to kind of skip a little bit details of Lempel-Sieve. I may mention something, but just to tell you that the Lempel-Sieve martingale is as good as any finite state martingale, not only in the success, not success way, but also on the growth rate. So actually, if S is not normal, then the Lempel-Sieve martingale has a very high growth rate. That would correspond to saying the Lempel-Sieve dimension of S is less than 1. Okay, so there is the S scale corresponds to a scale in the Lempel-Sieve martingale. Yes. Yes, for Martingale, yeah, for the lamp, but of course, I mean, it's not dimension. I'm abusing a bit notation because it's a single Martingale or single strategy. So but yeah.
So I was saying that this follows from the fact that finite state dimension is less than 1.
Yeah, this is the idea. It follows because the Lempel-Sieve martingale is always as good as any finite state. So it's optimal for finite state martingales in a very strong way. So it's not only a success thing, but it's just a bound thing. Sorry. Okay, this. And well, I was probably, if I want to get somewhere, I will not talk much about Lempel-Sieve, but in case you've never heard about it, the idea of the compression algorithm of Lempel-Sieve is a very pretty and simple idea. You take an infinite string and you construct a tree with this string in which you kind of try to, the patterns that you repeat, instead of writing the whole pattern, you write, I've already seen this in the tree. So this piece has already appeared before in the string, and this is represented in the tree with this number. So you kind of save space by, instead of repeating patterns, referring to previous patterns you have seen in the string. It's not a complicated issue, but I'd rather, if I start explaining it, it will take me 5 minutes, I'm sure. So let's see. So there is a Lempel-Sieve martingale. It's very, I don't know if it was written, but it's very efficient to compute it. It's time n log n, approximately. No, not approximately, but O of n log n. So just for notation, since I need to compute an absolutely normal real number, just use for a real number x, sec b of x is the representation in base b. And on the other way around, if I have a base b sequence, so a sequence on alphabet sigma b, real b of s is the real number represented by it. Since I'm going to be moving between bases, I'll need to use sec to go from reals to bases, and real to go from bases to the real number represented. How to construct an absolutely normal number? Well, the basic ideas used are not complicated. And in fact, if I was just trying to compute a polynomial time computable absolutely normal number, I would end up in like a minute just explaining you how to put together all the different bases. Each different base has a Lempel-Sieve algorithm, and then diagonalize. But I want to be extremely careful with time, because I want to reach time n polylog. So each step needs to be carefully done. And in particular, base change is not so easy, because base change seems like a very easy operation, but if you think about it for a minute, imagine that you're given a binary sequence, infinite binary, and you want to change it to base 3. What happens? Well, doesn't seem like a complicated thing, but often you will have two choices that you will need to keep like until the very end. So this is, if you draw it on the real line, that becomes more clear. Representing binary sequence means choosing among 2 to the minus n intervals. But then if you do it base 3, you are in trouble if you're very close to the borders, kind of. How do you know where you are? How do you know? No, well, you are in base 2. Okay, never mind. It's probably these borders that are complicated. Somehow, you may have to see the infinitely long sequence in order to decide between two choices, which is okay. I mean, you just need to keep a couple of candidates. But then imagine that in the long run, this is going to happen many times. So you have to be quite careful with that. On the other hand, this kind of uncertainty between several choices makes your life harder in terms of using standard techniques to move from one type of interval covering to the other. Okay, for instance, Martingales. Since we are talking about limb succeeding, the way a martingale behaves may be quite erratic, but you are succeeding if your limb sub goes to infinity. But then when you try to translate it into the different base, this is going to be pretty problematic. Okay, how you change coverage from base 2 to base 3 because of this limb sub behavior. So all this mixed with the idea that I want to keep time bounds very low makes this construction slightly more complicated. So let's see. For each base B, I need to construct an X such that the Lempel-Sieve martingale does not succeed. That's okay. We need to construct a single real number for every base. So of course, what I want to do is I want to translate the base B Lempel-Sieve martingale into base 2. What do I mean? Well, the base B martingale works with sigma B star. I want some equivalent martingale that works with the strings that more or less correspond to the sigma B. They will not exactly correspond, as I told you, because there are always certain uncertainties, but still they need to be pretty close. But for this translation to be possible and efficient, the martingale must be quite well behaving. And this good behavior means that I have to try to avoid this behavior. I want a conservative martingale that doesn't change very much its mind. Kind of, if you decide that this is good and you're growing, you don't go down very quickly. So this is the idea, how to construct an absolutely normal number. Let me at least try to give you a bit more detail. You transform the B Lempel-Sieve martingale into a better behaving martingale. You efficiently change base. Once the martingale is well behaving, this is more or less a standard. It's an interesting idea, but we have used it before. We efficiently combine all resulting martingales into one, and we diagonalize. You probably understand what it means to diagonalize, but I'll probably show you a slide. So each of these steps should be, especially 2 and 3, would be completely straightforward in a polynomial time setting. But if I want to keep time bounds low, I'll have to combine things very slowly. So I'll have to make sure that even if I combine things very slowly as opposed to polynomially, I still get the right martingale, and the diagonalization still gives me an absolutely normal number. But this is, so just to show you a little bit what I mean with transforming the Lempel-Sieve martingale into a better behaving one, I want one that kind of has a savings account. You never lose all your money. You have always, like, your money kind of steadily grows, maybe not much, or it doesn't grow at all. But what you don't do is lose completely your money. So it's more conservative. And another way of seeing it is just saying that I want a strong success. A strong success meaning that I want the limit to go to infinity, not just the limb sub. Okay, and this is possible, but because we are dealing with the Lempel-Sieve Martingale and the Lempel-Sieve algorithm, and this for this we'll have to get a bit more into it, which I won't do today. But if you have some memory of the Lempel-Sieve algorithm, it kind of relates to how you parse your input into phrases. So kind of doing things more conservatively means being able to do the same parsing, but not betting all your money when things don't go very well. Yes, make a bit of money when things go well, but not too much. But since the computation of this Lempel-Sieve parsing and Martingale can be done in time n log n, but not only for this particular input, but for all prefixes, this kind of helps. You know, somehow you don't need to redo computations very much. You just do them once, and that kind of tells you exactly everything that happens for prefixes. Well, I will not get into more detail, but we can construct a new Martingale that is a conservative version of the Lempel-Sieve Martingale for base B. So we are still in base B. We have a move. D prime of B still deals with finite strings over sigma B. But now, the non-normal sequences that are not normal for base B, that is sequences for which Lempel-Sieve dimension is less than 1, you have a strong success for those. Doesn't mean that you succeed exactly where Lempel-Sieve Martingale succeeds. That's not true. That would be harder to get within these resource bounds. But only for those strings in which I was succeeding exponentially, now I succeed strongly. So I kind of trade, you know, exponential success for maybe a smaller success, but strong, meaning in the limit. This can be done in nearly linear time. And now, well, once you have that, so we started with, let me just draw a small draft, and I'll finish here with this algorithm. So we started with Lempel-Sieve for base B. I transform it into D prime B, in which I could use a strong success. Now, this Martingale, since it has a strong success, it is slightly easier to change base. So I have now another Martingale, but this one is from base 2. And more or less, it succeeds on the reals where this one succeeded. Okay? So if you have a certain W in base B, changing it to base 2 could still keep the success. So once you have that, well, this is what is written here, but we probably don't need the details. But yes, this new Martingale succeeds on the binary sequences that corresponds to the real where D prime was strongly succeeding. The computations in this quasi-linear time and to the polylog, they need to be carefully done. And for instance, the computation we get for this base change Martingale, they don't approximate the Martingale very quickly. They only approximate it this quick. So for input y, I get an approximation that is at distance 1 over polynomial of y. That's far worse than we're used to in effective dimension, but still it works. So somehow what we learned is that if you get much slower approximations for Gales or Martingales, you can still do a theory, but of course your properties, they all have to be carefully tailored for this. So you can still diagonalize and have the usual properties, but you have to be a bit more careful. So so now what you need to do is put together all these Martingales. They are all in base 2 now, but they correspond to different B. So I like just to do this. So you have to do it a bit more carefully because you still want to keep your quasi-linear time, but this is doable as long as you take polylogarithm sums, which makes things slightly different from what we used to, as I tell you. And once you have that, you just diagonalize. What does it mean to diagonalize? Well, probably most people in this room don't need this, but by a recursive construction, I choose the next symbol such that this quantity, the d over x of n and this symbol, is the minimum overall possible. So you here, you have already chosen xn. You need to choose the next symbol to be 0 or 1 because you're choosing this is binary. You choose the one that gives you a smaller value. Okay? In that way, you make sure that the resulting infinite path is bounded. Okay? So you don't succeed. And the time you need for this is approximately, if for computing this Martingale unit time t, you multiply by linear bound. Of course, you don't want that, so you want to do it. Sorry. Fairness condition. Okay, sorry, I'm a bit confused now, but we managed to do it in quasi-polynomial time, okay? Given the martingale that corresponds to the union of all these Lambert sets. There's a detail now I don't see, but I'd rather not stop here. So all the steps were performed in nearly linear time on a common time bound that is independent of the base. That's why, so each of these, they were quasi-linear, but they don't depend on the b. And actually, in the very end, when I put together all the bits, what I do is I put together a logarithm number of b's, so I go very slowly with the union. So, well, let's see. So, just as an overview, we have seen that normality corresponds to the lower level of algorithmic randomness. So, there is just a detail that you may have known already that finite state randomness and finite state dimensions are not closed under base chains. What it means that if you write a real number in base 2 or in base 3, you may get randomness or you may get nothing. You may get a very predictable sequence. That doesn't happen for polynomial time. Okay, so polynomial time has been, I think, is the lowest that has been proven to be invariant under base chains. So this is kind of a challenge to see exactly where is the border, where things start to be base dependent and why. Okay, let me tell you a bit more corresponding to absolute normality before going to other people's work. The thing is, I explained to you that crypto people, they tend to regard this pi square root of 2 as randomness sources because they think they are absolutely normal. So can we substitute these numbers by our computed absolutely normal numbers? So yes? Sorry. What is... can we have sequences that have a positive finite dimension, but not one exactly? So they are not normal, but they have some normality in them. And can we have things that are biased normal in every base? Or, I mean, how does this look? When you, instead of asking for normality for dimension 1, you change this one for another value. The operation of base chains seems very normal, seems very elementary, but maybe we should, get a tighter time bounds about its computation. And finally, I explained to you that I don't know if he says Becher. Okay, Becher, Heiber, and Slaman. I'm going to take the freedom of saying it the Spanish way. They have an algorithm previous to this one, which is in quasi-quadratic time. And it's a very nice algorithm, very well, probably far more mature than ours. So, but it has an extra advantage, is that the discrepancy, meaning the convergence speed to normality, is very high. How high? Well, actually, they have a more recent paper in which they can kind of tailor it. You can get any discrepancy f. Of course, you don't get polynomial time anymore. You need to pay for this low discrepancy. They can get things in which there is some sort of exponential, low exponential, including f. So what happens is what they have proven lately, it seems to be that if you want to achieve normality very quickly, you need to pay width efficiently. So this is something that we should really find out if this is necessary. Can you get discrepancy for free? Or is there a necessary trade-off between how fast you're normal and how complicated it is to compute you? So computation time versus discrepancy. So we have improved computation time quite a bit from them, but our discrepancy is very bad. In all these steps I didn't detail today, I kept saying I need to slow down things. I need to take only logarithmic many terms in order to get my time down. Yes?
Just about question 2. So if I understand, something like, can you construct a real number that has finite state dimension half in base 2 as well as base 3?
Yeah, that would be an initial question. Of course, I wouldn't mind to have like every base, but yeah.
Yeah, I mean, relatively fine basis. That's the difficult case.
Huh. Some sort of absolute bias normality, yeah. Let's see. I'm looking for that, but I'm willing to pay like for intermediate results.
Are there any partial results?
Excuse me?
Are there any partial results known?
Not that I know. I know of separations between other randomness concepts, but I don't know of particular results there. I'm not sure whether this is possible. Maybe there's a way of showing that this is not possible.
I think it's possible for dimension, but impossible for strong dimension.
Oh, okay, it could be. Yeah, yeah. There's some intuition there. Yeah, strong means that you steadily grow up. Yeah, that could be. Yeah, that could be.
I mean, beyond initial intuition.
Yeah, that would be interesting to prove. Well, maybe then you can start trying to prove that it's impossible for strong dimension. That may be more doable. Yeah, I don't know of any result, but yeah, I'm almost sure, but I'll check once more and send you an email just in case. Okay, so about references, this is the paper I presented. This is the previous algorithm by Becher, Heiber, and Sleiman. And this is the new, let's see, 2017. Yeah, this is the second algorithm in which, as I tell you, I think they get as low discrepancy as needed, but by paying in time. This is the paper in which they rewrite Turing's node, and they get exactly where it's correct. I mean, they get it written like more readably. And then, why are we now so interested in normality? People in number theory have been looking at this concept for a while. So let's see, do they care about effective constructions? And for instance, I want to show you a couple of papers in which Becher and Juchman in one, and Becher, Heiber, and Sleiman in the other, they have proven number theory properties using this kind of constructions. What have they proven? In the first one, they have looked at something that is called continuous fraction normal numbers. So if you've ever looked at continuous fractions, they are another way of representing real numbers. You can also look at normality there. You can also look at numbers that avoid any pattern. So they have built a number that is both absolutely normal and continuous fraction normal. And they have done it efficiently. In the second paper, they have tried to achieve Liouville numbers. Liouville numbers are numbers that are very well approximated by rationals. So kind of the rationals that approximate them, they are very close. So they are able to build something that is absolutely normal and Liouville. This was completely unknown, that there exists one computable real number that is both absolutely normal and Liouville. And I mean, these people are working, still working on a number of number theory problems that I think can be.
So I shouldn't say this, but I have a construction of a linear type base 2 Liouville number. It never gets referenced.
It never gets. I'm sorry.
Nobody references this paper. I have a linear type construction of a base 2 Liouville number.
That is also. Is it a normal? Oh, when was this? Oh, you should send it to them.
And the gap is really huge because absolutely normal Liouville number is doubly exponential construction. So whereas base 2 construction is linear type.
And it's only binary normal, is it?
It's only normal.
Can you send me the reference? Or you should also send it to them, but I'll do that.
So there is an open question here, as in, can you reduce the doubly exponential to at least exponential?
You mean in this construction?
In this construction.
Yeah, I haven't really checked this one. This is, yeah. No, I know. The thing is that the authors were already very interested in the more recent papers, and I didn't talk much to them. I mean, I saw them in November, but we never talked about Liouville, or at least I didn't get it. Yeah, that's an interesting question. Yes? Oh, I thought there was some question. Okay. So this was all I planned to say about normality, and since I still have some time, I'd like to talk a bit more about what I was telling you, results in fractal geometry that can be proven using effective dimension. But, since if you want more questions or a different approach, I can also do that. Let me try to go quickly about just the beginning. I just wanted to show you here that, the original Hausdorff definition of dimension involves delta covers, involves, covering sets, and the diameter is vanishing. It involves the definition of this HS, which you might have heard about. It's called S Hausdorff measure, in which fractal geometry people are pretty interested in the measure itself. And then the dimension is defined by taking the smallest s for which this S Hausdorff measure is 0. So somehow for every set A, there is a jump for a small s. This S measure is 0, and then, is infinity, and then it jumps to 0. And like the jumping point is what it's called the dimension, and you probably know that in the jumping point, the Hausdorff measure can be any value. It can be 0, it can be infinity, and it can be a finite value in middle. And they are especially interested in the cases where it is a finite value. They are called as, okay, never mind. I presented, these days I've been presenting effective dimension. I told you a little bit that it is not necessarily 0 and meaningful. And it is not necessarily 0 and it is meaningful on singletons, okay, on one sequence. So that is subsets of one element, which is, of course, it's completely trivial in a classical case. Every singleton has measure, dimension, and everything 0. It coincides with Hausdorff dimension in many interesting cases. I will show you a little bit next of what we know about this. So they are simple classes, simple in the sense of descriptive complexity. They in this effective dimension and dimension are the same. And then it can be characterized in terms of Kolmogorov complexity. So these robustness properties I kept mentioning, they're very useful for us. So for individual points, as I told you, of course, I have been freely, without being very careful, talking about the dimension of a singleton just by saying dimension of X. Sometimes even I've been more worried about resource bounds, but I did see that. It has the property of absolute stability, meaning that the dimension of a set can be described as the supremum of the dimension of the elements in the set. This only happens for countable sets in classical theory, and well, it has to do also the dimension of the union is the supremum, but it has to be a countable union. So as I told you, for simple sets, for simple classes, effective dimension and dimension, they coincide. How simple? Well, they need to do, let's see here, any union of pi 1. They don't have to be sigma 2. It's any union of pi 1 has halves of dimension exactly equal to effective dimension. Okay, so this was already a sign that this could be useful for fractal geometry. It really depends on how complex the sets you want to get the dimension for are. If they're, well, this doesn't seem, I mean, there are quite a few nice examples out there that are unions of pi 1 or even less. Okay, so we are partially happy with this. And as I tell you, there is a Kolmogorov complexity characterization also for Euclidean space, you know, because in fractal geometry, they seem to be especially interested in Rn or Rm. So the Kolmogorov complexity at precision R is kind of a natural definition. That means that the Kolmogorov complexity of real X with precision R. It's the Kolmogorov complexity of a rational number that is at distance 2 to the minus R. Of course, you take the best case, the smallest KQ. So I don't know why I didn't erase this, because this for Euclidean doesn't make any sense. For other spaces, it may be interesting. So you also have that effective dimension can be characterized like this. So that's Kolmogorov complexity ratio. So once you have this, our research plan was to try to use this to analyze real examples in fractal geometry, point-wise analysis of dimensions. Well, we try to tell them, you know, for certain classes that are simple enough, I'm going to give you the exact dimension that's going to, the effective dimension that is going to coincide with what you're looking for. And I can do this in a point-wise way. I can analyze the dimension of the points in the set, and then this will give me your classical dimension. Extensions to computable analysis, I will not talk much about this today. So, for instance, what we have done, we have looked at self-similar fractals, random self-similar fractals that are not as easy as they may seem at first sight. There are many ways of defining them, and, well, they are not so easy to deal with. For all of this, we've been able to look at the dimension of the points in the sets. Okay, trying to see if there are points of very low dimension, which is the highest, the lowest, how is the range, can you get everything? And also, people have looked at the dimension of points in lines in R2. So only on the plane. This seems to be like a very, how do you say, a specific problem, but it turns out to have a lot of applications regarding open questions in fractal geometry. They are worried about things like Kakeya sets, which I will not probably define. I don't know, but they have to do with lines, and in the plane, something is known about them. I mean, so the dimension actually is known in the plane, but it's not known in higher dimensions. So somehow, it seems that at least understanding the plane first is the way to go, because looking at lines in R3 is pretty complicated. Like looking at the dimension of points in lines. Okay, so which is like whether they are very easy to describe or they are very hard, how hard can they be, etc. So still, I mean, yeah, okay, you try to convince people, you're going to be lucky, or maybe effective dimension is what you want, why do you want classical dimension, blah, blah, blah. But then what really I think made this particularly interesting for people in fractal geometry is that we can go back to fractal geometry. And there is a very recent result that I really like. that I'm not sure I can really present appropriately, because I think this is really a changing issue. It's called point to set principle. And it kind of tells you you only need effective dimension. You don't need classical dimension anymore. Why? Because for every set, here it says infinite sequences, Cantor space. It is exactly the same for Euclidean space, doesn't matter. The house of dimension here is got to do with the effective dimension when using oracles. Okay? You just need to look at every oracle. You look at the effective dimension using that oracle. You take the best case. This is your classical dimension. Okay? So I really recommend you to read this, the proof of this theorem. It's really neat. It's strongly based on the fact that we can characterize effective dimension using Kolmogorov complexity. Okay, that's descriptive theory. So it kind of explains you know, that in order to get a dimension result, you bound the dimension, you kind of get how good are the coverings that gives you this dimension. So in order to translate this into a effective dimension, what you do is you kind of, the oracle kind of has the covering for free. And the effective procedure is like looking at the covering as much as it needs. So for people that are used to dealing with Kolmogorov complexity, the beauty of the argument is like the way you codify something as different as a covering, you know, and I mean there are several levels in the cover, in something that can be accessed by a Turing machine. It's not a long proof, but it's a bit complicated to follow. But just if the main idea in mind, I think it's readable for almost everybody. So what happens is that now we can use Kolmogorov complexity. Sorry. I'm sorry, I didn't. CDIM. Oh, sorry. Sorry, I made the notation. Okay, I'm sorry, the notation is not completely universal. I'm sorry. This is dimension using lower semi-computable Gales or Martingales, if you prefer. And this is house of dimension. Maybe I should have written the H there. So house of dimension is just the classical house of dimension. Yeah, this is, yeah, I guess this is. I'm sorry? Okay, yeah, and it's also, there's a nice thing, it's a minimum because you really can get an oracle.
That's the thing that's surprising.
That's also very neat.
You'd expect in FEMA if it existed, but why should it be a minimum?
Yeah, so they see the coding is good enough. You are not just approximating, you're really getting it. So it's, yeah, I recommend reading the proof. I think most people that are interested in Kolmogorov complexity or this kind of methods will really enjoy the proof. I really like it.
It's kind of an analog that a continuous function is exactly one which is beautiful relative to an oracle.
Yeah. This is the idea. Yeah, so I think the flavor is the same. But I really like the idea that now, you know, since there are so many open problems from just which is the dimension of these sets, now you can rephrase them into computation problems.
Is there any dual of this?
I'm sorry? A dual. You mean for strong dimension?
No, okay, that's another question. I'm saying, you know, you can talk about the dimension of the individual points D.
Uh-huh.
Can you say something about the dimension of D with respect to E?
You mean look, oh, I see, changing, you mean he wants to change B and E? Is that correct? No, that's a good question. No, I haven't thought about it.
I don't know what it means.
Of course, B is a singleton. Yeah, sure. Yeah, that's a very good question. Yeah, I don't know. I like to know the answer. Maybe it's an easy answer, but I don't see it right now.
Maybe there is a dual because
Huh.
going from R and
Yeah, and about if you, instead of looking at Hausdorff dimension, you look at the dual, which is called a packing dimension, in case you have heard about it. I think the result holds true. I mean, because really the coding of the curve, I mean, you have to be a bit careful. You need to use the dual characterization because the coverings are a bit more complicated for packing dimension. But I think after, this result in which packing dimension was kind of dualized, I think that should be doable. Yeah.
So I mean, the interesting thing is always that you'd think that, there's some B that would be able to do, de-randomize things, but if you have a relatively random point in there, then when this one goes down, this one goes up. So
Yeah.
it's kind of weird stuff.
Yeah, it's interesting, yeah. Could be interesting, to see how it affects every point in the set somehow, the dimension of points there, yeah. Okay, I like to show you a couple of results in fractal geometry in which they have used this, and then I'll stop. Just to see that they are there. I'm not sure if I can even read them, but for instance, there was an intersection dimension calculation that was known only for Borel sets. Borel sets are a particular, I mean, they are, well, okay, the closure of open sets. And this was proven using effective dimension. For any set, it holds, and it was not known to hold. Another result has to do with Furstenberg type sets that I will not define. They have to do with kind of having every line in the plane should be included in the set, except that it's not quite every, because this is the restricted case. Never mind. But it was an unknown result. The Hausdorff dimension of these kind of sets is not known. There was a lower bound, and now this lower bound has been improved using effective dimension. And there's something called the Kakeya conjecture that's got to do with the dimension of Kakeya sets. And, that hasn't been improved. That was already known for the case I was proving, but kind of gives hopes of getting a bit higher in the conjecture. It is a conjecture about sets in different Rm for different m, and only the case 2 is really well analyzed. I mean, the dimension is known. So maybe hope to get new results for this conjecture, for higher levels of R. And this is particularly connected with learning or analyzing the dimension of points in a straight line. So this seems to be like a very simple question, but the answer is very far from being simple. So just knowing, being on a straight line, how high can the Kolmogorov complexity of the points in the line be? That's very informative for dimension, for fractal dimension questions. And I think I'll have to stop here, even if Rod asked me to talk about a computational complexity, but he'll forgive. It is in the slides. I am very obedient, so I put a few slides on the on NP complete set, so you can read them.
The first result, it settles a problem that a lot of people have tried. I mean, Joe Miller.
I didn't know.
Able to solve it.
Okay.
That solution is very elegant.
Yeah, it's the kind of solution that people used with Kolmogorov complexity arguments really enjoy. So.
Yeah, like the last one, modulo the point to set principle. Once that's proved, the last theorem is half a page.
Yeah.
And the original proof is several pages, So people in the area share.
Yeah, I just wanted to show you.
I know it's there,
No, sorry. No, I didn't mean that. Well, of course, the references that you may have a look, they include the point to set principle is here in Stacks 2017. And these are like the two results. No, that's actually the three results that have been proven using it. I didn't have time to talk about other spaces, but all this makes it interesting to look at other metric spaces. You can also have like this Kolmogorov complexity characterization plus point to set principles. So I just wanted to stop here. I try to give you an overview of effective dimension. Please keep in mind I was especially interested in resource-bounded effective dimension because next week we're going to have a whole week of algorithmic randomness in which I'm sure that the more computability-oriented effective case is going to be. So thank you very much. Please email me if you need further references. And thank you.